particularly delighted. We're kind of here at we always like to talk about pivotal moments, but I think this is a kind of a pivotal, interesting moment that for quite some time, we at the foundation have been interested in learning more about the interaction of fishes, particularly juvenile fishes, and nearshore environments, and have sort of wondered about a lot of different issues in an urban system like New York Harbor, when you begin to put piers and pilings, hardened shorelines and bulkheads and so forth, and what that means to the fishes and the fish community. And I guess it was close to 30 years ago, we sort of asked the question in the post-Westway era, and those of you that don't know what Westway, you probably weren't born then, but I'm not going to go into a Westway story at this point. But there was an evolution of regulatory actions that in years gone by in areas like Battery Park City, across the street, people filled in the river. It was a thing to do. You declare the river non-navigable, fill it in, and build housing and so forth. Well, that's not the case anymore. And but as we went from kind of the filling of the city to the waterways to other kinds of shorelines, we begin to wonder what makes sense. I mean, can we still encroach? What about the encroachments that have been made? Are they beneficial? Are they adverse? And we had a conference at the old World Trade Center about 25 years ago to pose that question, and came up with no really good answers about how one would go out and study these structures, particularly, how well do fish survive and under piers. Difficult environment to study. So after we had put in a great amount of thought, of months and years, and wrote up a report, we got a call one day from Ken Abel, Dr. Ken Abel from Rutgers, who said, I've got an idea about how you might look at things under piers. And from sort of that phone call over the next 25 years or so, we've moved greatly, at least the Rutgers folks have moved greatly into a better understanding of those relationships between the structures in an urban setting like New York Harbor and fish. And to our credit, I guess, or to the benefit of the region, Ken Abel was able to work with folks at NOAA and attract young researchers. Back then, young researchers. And looking at his resume, got his PhD 20 years ago. But anyway, there's certain people that got attracted to doing this kind of work, and there's very few fish biologists that are out there that are doing the kind of work that you can hear about today. So I think we're going to hear a part of 25 years worth of work, or a part of even the last couple of years worth of work, but I think some important parts, and we had asked Dr. Grothues and Dr. Abel to, 2 years ago, to start thinking about putting together a synthesis report of all the work that had been done, so we have a better understanding again of those relationships between fish and hard structure in the harbor, but also as not only to understand that for the sake of understanding fish communities, but to inform restoration into the future. So we're kind of excited that we got to this moment. This is one talk and one analysis, and I'm sure we'll hear more. So we're delighted to have Dr. Thomas Grothues here. Tom, again, is better known as Motts to his, I think, his friends and colleagues, which he can tell you about how he got that name. But he's an associate research professor at Rutgers. He makes his home, I guess, down in the area of Tuckerton, near the research center at Rutgers, and we're delighted that you marched up here to tell us a nice story. Dr. Grothues.
Thank you. And as Dennis mentioned, I'm going to say we, but a lot of this starts with Ken Abel. I'd like to frame this into the research picture going all the way back to the beginning of that. So I wasn't here when Ken started that. I came on the scene here maybe 15 years ago or so, but I'm just going to say we to make it easy. There's Ken's name there, so you know that Ken is instrumental in this. I'd like to start with this amazing graphic from Eric Sanderson's book, 2009, Manhattan, that shows the transformation of actually Manhattan and also the New Jersey side. The way that has changed here in this reconstruction. You can see there were marshlands here. They were even more extensive on the New Jersey side because of the geography of the land, the rock versus the sediment. But this place now is a place for people. You know, people ask me about that. I have no apologies about that. It's a great place. I love cities. They're actually very good in terms of for both people and wildlife, and people need habitat too. And this is perhaps a really good way to go about it. It makes for great economy to concentrate people, and the flow of goods and energy is benefited. And it also can benefit wildlife because it's an alternative to sprawl. One thing about this particular city, though, is that its location happens to be a very crucial point for fish, especially because of where it sits along the salinity regime of the river. This particular chunk of river here is ideal as nursery habitat and as overwinter habitat because the salinity is a regime that is not osmotically stressful. In other words, it's well balanced for a number of different fishes, such as striped bass. And the fishes that use this nursery, at least in its original state, come from as far away as the Sargasso Sea, South Carolina, and also even up north, Maine, and the coastal ocean here, but also from upriver of New Jersey. So it's a nexus for a lot of different places, fishes potentially. And so when we think about building the city for people, we can understand that that if there's a way to continue to build it out that's beneficial for wildlife at the same time and fish, of which we are users ourselves, that we should think about that. And so we have to look at the potential for habitat here and what it can do for us. So it was built up very early. So this is the turn of the century, is given away by the type of steamboat paddle wheelers here. I saw this picture in the subway someplace on the wall. It also is from a book. I don't know exactly where it was, took the picture, but you can see the development over here of the infilling of marshes, especially over here on this side of Newark Bay, but also on the New Jersey side, especially from 1900s through to 1989, and this comes from a 1992 paper. And so that's lots of marshland, but it also altered the shoreline in different ways. Even where there wasn't marsh, it changed it by hardening the shoreline and changing the depth of the water near there. And as Dennis said, we wonder how that impacts fish habitat. So these types of changes were important because of their service to humans. Obviously, transportation, people get drinking water from rivers. They still do waste removal here. Well, it's treated now. Irrigation, industrial water, fisheries, access, defense, recreation. I have one there for fish too. Maybe that's coming up next. But these are the types of shoreline modifications you see: bulkheading, which happens along very deep shorelines, high energy, riprap, so we know what we're talking about coming up here, and this is in Brooklyn Bridge Park. piers, structures on piers, barges. So those same shorelines serve fish, but it's very different now. Here you see Manatee or Atlantic silverside in very shallow water, and they move up these very shallow creeks into marsh habitat in very large numbers. So to them, these shallows provide refuge. They tightly couple your benthic primary production, especially from marshes, which is very, very high, to fishes through a detrital-driven food chain. So the fishes aren't eating the marsh grasses, but the marsh grass becomes detritus, gets broken down, and fish benefit. Access to marsh pools, so many of these fish move up into pools, so they actually cross the tide line to lay eggs that are left with the retreating tide. And there's access, of course, to structure. And so an overview of the talk is that I'm going to go into a review of our earlier work with Ken Abel on looking at these structures, the shoreline, and then look at some recent works that I haven't talked about here. Some of these have just recently made their way through peer review publication, are in that process now, and we never gave a seminar on that material now. So that means that I have to skip some of the details of the stuff that we contributed to earlier. I'll gloss over it, and I'm not going to go too much into the data because at this point I want to talk about the larger picture. And that's what I mean by this data-supported perspective in the next steps. So going back to 1993, Ken began looking at pier use by benthic fishes, and this was prompted in part by the Westways investigation. And really, there was a number of projects there that surveyed fish under piers, projects that caged fishes under piers and away from piers, and in habitats that were relic piers, in other words, pier island fields where the pier had collapsed. And these things are meant to decompose the structural effects from shading effects that piers have, because there are concerns about how to build piers, particularly relevant to shading. So then, again, that was benthic fishes, fishes that we associate with the bottom. And those types of things are typically done by caging and trapping. But the more mobile fishes are very, very difficult to sample and analyze, especially when it comes to different habitats, because where you would sample with a seine in one condition, you can't sample with a seine against a seawall or a bulkhead. Fishes that are up in the water column aren't fishes that would enter traps. Again, you can't fish a gillnet in very shallow water where you could against the pier. And so we started the use in 2007, I think, with Hudson, which is a particular type of sonar that's narrowly focused at very, very high resolution. This is dual frequency identification sonar. That came out of pre-9/11 efforts towards harbor security. And that looks, I'll show you a little bit about that later. It looks like an underwater film, kind of grainy film. And that is a much less biased way of understanding the distribution of pelagic fish, because you can see fish moving around that you don't have to catch, and it doesn't matter if it's dark or light. So we focused on those for a while we had this Hudson available to us. Moved along to look at not just piers, but other types of shoreline habitats with Hudson as well, and finally came back to very shallow shoreline habitats where Hudson was no longer feasible, because we're starting to look at benthic fish again in habitats that are essentially restored since the time we began, or have become relict and reappeared since the time that we began this. And I'll talk about those questions. So here is one of the texts Hagen in a kayak paddling through a relic tile field. This tile field has actually been built over the top of now, because this one is adjacent, I think, to Pier 40 on the side here. And you can see right here he's got basically a tote with a laptop on it that he's watching this sonar, Hudson sonar that's strapped underneath. And here he is coming out from underneath Pier 57 with that same unit. And so that's how we were able to look at, and you can just see the shadow of that Hudson sonar, which is about the size of a large coffee can or so, strapped down below the boat. And in real time, that's showing on a screen here. And that was coupled with ground truth, because the images, as you'll see, don't let you always or infrequently let you identify species. Instead, and this is a repeating theme when we're working with the Hudson, we have to work with categories of fishes like bait fishes. And some of these things you can tell apart. I'll show you again pictures. These clearly are striped bass right here. They're very broad between the eyes. As this is normally viewed as a movie, and that movie is actually very diagnostic of the fish that you see. So it goes well beyond simply a static image like this. You can see the way that the fish swim. You can see them erect their two dorsal fins and put them back down in the way that striped bass do. You can see the way that the tail flexes, how deeply it's forked. You can get up on these fishes sometimes very close and get a high detail, but you can't see color. So for instance, you couldn't tell this was a striped bass unless you knew where you were and that this big one was a meter long. Then you can start putting things together. Bait fish, on the other hand, these are Atlantic menhaden. Again, if you're not used to looking at this, it's kind of like walking along a forest path at night with a flashlight. You see the bottom or the floor in front of you is a patch. There, that's lit. The air in between you is not, well, it is lit, but it doesn't reflect light until something like a moth or something flies in front of your flashlight beam, and then you see the bright spot of the moth right there, but you also see the shadow of that moth on the spot that you're illuminating. So these menhaden are just above the bottom a little ways, and you're seeing their acoustic shadow. It's not a light, of course, it's an acoustic shadow you're seeing beyond that, and the perspective here is somebody walking that way and illuminating and again, when you see this as film, you see these fish swimming, you can count tail beats and things like that. You can see differences in the way that fish behave in types in both the size, but also the distribution. This is what we call an aggregation of fish. These happen to be Atlantic silverside, and we're able to actually, this is from ground truthing, visualize these fish and watch them while they're in the Hudson beam, because we've got it anchored near a dock and we're actually watching the fish as they're swimming underneath. And these are smaller Atlantic menhaden, and they're characterized by characters of the individual fish. For instance, the aspect ratio or the height length, but also of the swimming pattern, and of course they're among members of the group of fish. So this is an aggregation which you would notice in the moving frame. They're not organized to each other. They're all in the same area and they're moving, but they're not orienting to each other in the way that these fish are. These fish are maintaining this constant kind of near constant spacing to near neighbor and a similar orientation. And those are clues to what kind of fish that you're seeing in there. And that's about the level that we could confidently classify many of the fishes that we saw. Other things like eel, American eel, which is the only eel you'll see up into the fresher. You might see conger too, but eels look like eels. There's not much mistaking them. Flounder, but you can't tell a winter flounder from a summer flounder. blue crab, you could see them in amphiplexus. You could see horseshoe crabs and identify those as species because there's only one. But they show up, you know, and you can see them during mating with several males behind them and stuff like that. And oyster toadfish you could see, but also a lot of the benthic things tend to be cryptic, like oyster toadfish could be under a rock, and you would miss that with a DIDS or just be hidden against the background. So it's a little bit limited. We have to classify into these classes, okay? But in general, let's talk about, I skipped over that pretty quickly, but I just want to give an overview of the results of that before I move into this next phase. So what we found from trapping and various other kind of net surveys underneath piers, we found that benthic or bottom fishes were actually much less abundant or absent under piers. The exception was fishes that are commonly found to be nighttime feeders. American eel was the single species that was more abundant under piers than adjacent to piers in structured or open water. There were some other species that were more abundant in open water, but not like so rare under piers. And again, these were things that were olfactory feeders. Tom cod, which have barbels and feed by tasting in mud. The other part of this experiment was that when you caged fishes, this is a group of fishes with different life history traits, you caged these fishes under the pier, you caged them alongside the pier, and you caged them adjacent to the pier in open water. Fishes in the open water grew and lived, and fishes adjacent to them alongside the pier grew and lived, but not as much as fishes in the open water. And this is over a period of months, by the way. And fishes under the pier either degrew, actually shrunk, or died. And again, the exception was your fishes like eels, which are olfactory feeders. And then looking at the mechanism of that, by looking at the bottom where these fishes were caged and the fish's guts themselves, we found that the principal reason for this was likely to be a lack of being able to feed or being stimulated to feed when they're in the dark. So there's actually more invertebrate prey underneath the pier than there was outside the pier where these fishes were growing. And that may be because they're not being preyed upon. It's essentially a refuge. But for one reason or another, the fishes that are visual feeders, they cannot see under the piers or were not stimulated to feed under the piers because of this lack of light. So their guts were not full, even though there was plenty of invertebrates in the ground there for them to eat, and they were invertebrate eaters. The problem is here, though, that doesn't mean that fish don't go under the piers. That means you can't keep them there for months. It could be that same fishes have maybe utilized those piers on a very short-term basis. If you do a heat map of your house, of where people go in your house, you might find infrequent use of the bathroom, but the bathroom remains really, really important part of the house. So we want to still understand how that fits in. Like we can't say from that experiment that piers are evil or something like that. Only that that fishes don't tend to go under them, and we know why. They are detracting from the habitat from shallow water habitat in terms of the ability to forage. There's no doubt about that. And it seems that foraging is one of the reasons that these small fishes use estuaries as opposed to other places. They're really, really productive, and you're knocking off that productivity application when you shade these. So again, this pattern did not hold for unshaded relic pier structures, so fishes that you caged there did fine. So again, a clue to the shading as part of this problem. When we started looking at the large fishes to see if there's a pattern there, similar to the small fishes, we found that, or benthic fishes, we found that pelagic fishes also declined deep under the piers, but there was the large fishes seemed to use the pier edges as feeding habitat for ambushing. And we actually watched on Hudson as fish came out, large fish like bluefish and striped bass came out from that pier edge and attacked fish that were in open water that presumably can't see them. And fishermen already know this, but this is part of data and you know, actually documenting that kind of. As a result of that earlier work, there were a number of policy changes, recommendations, and actual physical changes to the way that things were being done in this part of the estuary. And they're pretty interesting. I really like them. I think they're innovative. This is at the Wall Street C Street, or near the C Street dock there. These types, so this pier here has open space to actually make the pier edge ratio, so the surface area greater so that you're always kind of near the edge, which is habitat that fish are more likely to use. Even where you do have covered walkable space, you're now seeing grading, and the new piers being constructed or renovated as parks have these connections to the street, and I've heard them referred to as able grading. I don't know if that's widespread, but people have talked to us about the able grading that they have there, and I think that came from the fact that these are influenced by Ken Abel's work on shading early on. And especially at the connections to the street, these are really important because there's a number of fishes that follow shoreline and maybe don't go all the way around piers, and this allows those coves to connect, so to speak, connect to shallow water, because these piers often run all the way out to deep water. Here's just another example of that. This is built over a relic pier here, and even the railings are slanted so that they cast less shadow onto the water. But then, of course, there's a lot of innovation going on. There's things we didn't look at, like these very small things, small floating docks, and piers or barges are being frequently used because piers, it's hard to get a pier permitted, but there's barges around the place. So do they matter? And we went on to look at barges. Barges are different because they are mobile. For one, they tend to be much smaller, and they don't have supporting pilings underneath. So the question is, were they different than piers? Again, we had to address this for at least pelagic fishes as groups instead of as species, because generally we couldn't tell the species. But for three types of fish separately, we found that large fish, which tended to be striped bass and bluefish, I think we saw like black drum once, we have no measurable response to barge state. But really, these things were just really, really scarce in general. And for the limited amount of survey that we could do around barges, the stats it just doesn't have the power to tell you much. But we did see, and it's a clue, that these fish would just swim right through the shade line. So they'd go in one side and out the other. And presumably these barges were just, like, you could see the light at the end of the tunnel. They're small enough you could see clear through, right? Small single fish preferred barge shade, but it was conditional to the mooring location. So what we found was when the barge was moored along a pier, and this is what's the name of it? Yeah, Lehigh barge, okay, which is a museum education thing. So that was actually moved. So we got to go to these locations before, when the barge was there, survey the same place after the barge was gone, look at the new place where the barge was, and survey that place before the barge was there. So we got this neat little experiment there. But basically, if the barge was moored alongside a pier, there were fewer fish under the barge than in the open water. When the barge was moored alongside a breakwall, we saw more fish under the barge than in open water. And there's a couple potential reasons for this. One is that the mooring location, the environment that you get when you have a riprap, essentially a cove, a closed environment, holds the kinds of fishes that are more likely to go under a barge. The other potential explanatory factor is that when you're moored alongside a pier, you already have all the shade you need. In other words, it's shaded, and fishes that need to be or want to be under shade are under shade, and don't need to go under the barge to get it. And for schooling fishes, we found no measurable response to barge shade, but did respond to position alongside the barge. And that was relative to the front of the exposed side of the barge or the back side of the barge. And principally, these were Atlantic silverside, but we also saw that some of these were, by actually observing them from the water, some of these were small Grothues, so probably juvenile Atlantic menhaden and or things like Holocene shads. Okay. So, in effect, that was becoming shoreline form. And we know that schooling had an effect for piers too. It seems that when fish school up, they're paying more attention to their nearest neighbor or the school than they are to the particular habitat. So we saw these huge schools of fishes actually crossing all the way underneath piers. So they moved from the ocean, from the open side north of the pier, through the pier. So there was fish in open water on both sides and solid fish in between underneath the pier, and then eventually out the other side. And I think that smaller fish or smaller groups of fishes, as they approach a shade line in the water, may become wary of it. But if you have this big school that you're dedicated to, if that school begins moving under the pier, it seems to stay cohesive, especially because many of the fish may still be in the open water and not threatened by the shade, so to speak. And so the school stays together. And of course, that's my interpretation. We don't know what's actually going on, but it's an observation of cohesion that seems to mitigate the shading effect. Okay, so the question is that came up with these piers is that they actually shade relatively little habitat when you look at the river, and especially barges even less so. By the way, how much time do I have left?
Half hour, 20
Okay.
minutes.
So the problem here, though, is that only a portion of this wider area is suitable as shallow water nursery habitat to begin with. Can't really count this whole river bottom as nursery habitat because that's not the kind of habitat where those species are found or those stages are found. And we're particularly concerned with juvenile fishes because juvenile and fishes are the fishes that set annual growth curves, right? So mortality in these fishes, in these marine fishes that we're seeing here is typically greater than 99%. So you'd think that a change of another percent or so doesn't seem to be much. But if you look at the survivorship side of that, that's doubling survivorship. So this is where recruitment and year class strength for fishes is set at this stripers that are moving around that people are catching, because you don't get those if you don't have the nursery habitat. So I said, well, this really is, you know, if you look at it this way, you're starting to cover maybe 30% of the available habitat. And we'll come back to that because that's not quantified yet. That was at the time like, okay, what does that really mean? So we're working on that now, and I'll kind of wrap up with that at the end. Just let me say that this is a real concern elsewhere. It's being addressed elsewhere. This image comes from a plan in Vancouver, but all along the Pacific Northwest, especially Seattle and Vancouver region, where you have a largely urbanized estuary. The concern is shoreline fishes and especially salmon. Now, if you've been to the West Coast, salmon up there contribute a huge chunk to the economy up there, and they're rightfully concerned about salmon moving out through the rivers. And shading became a big concern because they saw salmon smolts won't pass under the shade. So they started doing things like building what looks like a natural slope and reef into the habitat over there. But we have a very different system. This system here is the nursery habitat is not dominated by reef habitat, but rather by soft bottom habitat and marsh. And marsh is just gone, and it's much more difficult to build into infrastructure here. So we've learned a lot from the West Coast, but we have a unique set of things also, a unique set of circumstances. This is an image of from inside the restoration at Liberty State Park alongside the Liberty Golf Course, where there's a mitigation that beautifully restored some shallow water habitat to add marshland there. And that is thriving. I mean, that is thick with fish in there, and I'll talk a little bit more about that. But there's other places along this stretch on both sides of the river, especially on the New Jersey side, where there is the possibility for doing restoration. And there's also the possibility for just relics of these nursery habitats that remain that could potentially revive the system as kind of seed areas. The question is, are they useful as habitats? So they maybe look good, but already back in 1976, a paper by Bone describing the development of piers mentioned that the early development of piers in this area was earthen extensions out into the water, bulkheaded earthen extensions, and the water behind them that was in the coves that were formed by them became stagnant and nasty, and that was one reason that they moved over to these piers with pilings so that the water could flow through and flush. And they also tended to shoal in. And so we saw a move towards these kinds of piers. Well, a lot has happened with the water quality in the Hudson River since 76, when probably it was near its worst, 72 or so?
Go further back.
Okay. Certainly before the Clean Water Act. It's no surprise that those areas became stagnant. It's possible that many of these other manufactured coves that still remain as earthen dike areas would be stagnant. So looking at them, they have this ecological equivalent as coves of the areas that used to be here as marsh, but there's no saying that that's actually the case until you go and look, because do they even have the right salinity temperature and especially dissolved oxygen regime of those areas? Well, this restored area certainly did, but we ought to go take a look at all those kinds of areas, and many of them are unplanned. So here, for instance, is a sand beach that's forming off of, and we watched this grow over a number of years. This is right off this side of Governor's Island, right? And there's fish there. So we seined this area and we caught larval or juvenile settled winter flounder and Scophthalmus window pane, another flounder, and a number of other small fishes in these very small habitats. Now those habitats and those fishes are supplied, like I said at the beginning, by broodstock that may be outside the system or outside the harbor, even if they're in the system, like striped bass and white perch are spawning upriver and freshwater, but those larvae get here, fish from offshore get here. So what about things that are locally spawned, like mummy chog? The question is, can they establish in these areas where you have small pockets of marsh, because they're obligate to be marsh users. So we started looking at areas, other shallow water areas, which were either naturalized. None of these places are natural anymore, but returned to a somewhat natural state, either intentionally or accidentally. And they have a number of structures. So first we're interested in these structures outside of piers, riprap, and bulkhead. But we chose locations where one location had all of these different things. Like Brooklyn Bridge Park had riprap and bulkhead and pier. And Governor's Island had some of all of those things when you tucked inside where the school landing is there, and so did Liberty State Park. So we looked around there. Again, we had to use Didson for some of this, and here you see along a bulkheaded wall. Here you see these big cobbles. Here you see this very small cobble riprap instead of the big boulders, and here you see a natural sand bottom that's pockmarked by biological activity. And we looked to see what happened with distance offshore of these. So these are essentially kayak transects at 2, 12, 22, and 31 meters offshore. In some cases, as you go offshore, it gets deeper. In other cases, it's simply further off the beach. So it's a proximity question. Also, we went to the Jersey Flats, where we had similarly shallow water, but you had no shore. So that can help decompose the difference between between having a shoreline and simply shallow water. And again, we had to do this with Didson because there's no way to sample all those kinds of habitats with the same kind of fishing gear. And again, here you see differences in school classes or types of classes. I'm going to move to this side. It's easier to point. Okay, we found that there was a lot more fish in some locations than there were. In other words, the location effects seem to be stronger than the distance offshore effects or the type of shoreline that you have. But that changed between years. And the reason for that change was largely because the second year, 2012, had a lot more menhaden. There was some massive menhaden recruitment that year, and we're seeing lots and lots of menhaden, and they act different than some of the other schooling fish, and explained that. So we haven't removed those out to see what happens yet, but I can tell you that it explained a lot. Because of this, I'm not going to show you series after series of these bar graphs. That would be just horrible. So I tried to condense that into this PCA, principal components analysis. If you're not used to looking at those, consider that each of these symbols here is a sample taken by Didson at some place. And stations or samples that are plotted very close to each other have the same concentration and types of fishes in them. And you can see what those fishes are and how much the concentration is by the direction of the arrows. So these ones out here tended to have large schools, small pelagic fishes, typically silver sides and anchovies. stations here tended to have benthic fishes and not very many schooling fishes. And the ones out here tended to have aggregations of small pelagic fishes. And one of the things you see, because of the fact that these are color-coded and shape-coded to particular structures, is that you do not see a clean separation of those. You do see three kind of groups, but you don't see those as a function of type of shoreline. Distance from shore, again, this really seemed to matter, but when you add it in the second year, it no longer mattered because Menhaden changed that equation. What mattered was when you took the sample. So this whole side is nighttime or daytime, and this side is nighttime, and here you have a mix. So benthic fishes, they're not changing their distribution much by day or night. Pelagic fishes were, but it's probably actually the same species doing a different behavior. And this is supported in the literature that small schooling fishes will bunch up during the day for protection and then spread out at night. What did turn out to be very telling was the water velocity. So we had current profiles from an acoustic current Doppler profiler running along all of these sites. I'm just going to show you two of them. So this is the bottom, and it's not because the bottom is particularly rugose here, but because the boat's going away from shore and coming back to shore and going away from shore. This is the path of the boat, and this is where it's doing that. So starting all the way up in here and coming out here and going along there. And what you see here is the water flow is uniform throughout here and very, very slow. It's on the order of 1 to 30 centimeters per second. Okay, very slow. As compared to this area off Brooklyn Bridge Park here, this is along this bulkhead, where you have over a meter per second flow. When you looked at the distribution of fishes relative to flow, it turned out that these coves were very, very important. So a cove that had more flow had less fish, but still had more fish than open water, and the coves that were very, very still had the most amount of these small fishes. Now, in the Hudson, where you really are lacking marsh habitat, you have very, very few places for mummichog. The base forage fish becomes things like anchovy and Menidia, Atlantic silverside. So this remains very important as habitat potentially for those kinds of fishes, and you also see more benthic fishes in those low flow habitats, regardless of what they're along. But still, well, I just said that, so move past that, because there's one last thing, two last things we want to do. What, I have 10 minutes left now? Something like that? Okay. So there's a number of these very small embayments. They're very tight, and they were dredged out, and they're bulkheaded typically on all three sides, but they're natural sediment traps, because water enters them at higher velocity at high tide, exits at a lower velocity, so sediment tends to settle out. And as a result, they trap sediments in the back of these when they're not maintained, become filled in. And as shipping and various other shoreside commerce has changed location, some of those places have been abandoned, and they now actually have spartina growing on them, and other types of high marsh vegetation going upslope. And they're beginning to emulate some of the places that have been restored, like Liberty State Park. So the question is, they're beginning to look like marshes. Do they maintain marsh fishes? because the question again is the water healthy enough back there for it? And if a population was eliminated there earlier, can it reestablish? Things like mummy chogs don't travel very easily across open ocean or across open water, and moreover, they have larval stage that puts an egg, as a sessile egg, that's glued to things like broken off stems of grass and or broken up open stems of grass or rib mussel shells and stuff. So they don't have the pelagic distribution phase that some other fishes do. So are they back there? So we began serving those. And this is Global Marine Terminal right here. Here's the pool lady barge. Here is some of this background. Some of these were steepened by riprap, but still had flooded vegetation during different parts. This, I think, is at the same place, the back of that marsh at low tide, and you can see Spartina here, but also different structures up here. So we trapped and seine here, and also put up pit traps. So these are, you basically go up here and dig in a casserole dish, and as the tide recedes, those act like natural depressions that fishes that are natural larval retention areas for fishes that go up onto the marsh, like mummy chog. And we dip netted around these too. This is at the Coast Guard embayment south. Another section to the north and over here changes a bit. A very different beach, but in the same embayment. And these typically had fence along the side, upland side, so you can't access them by land, only by boat. Although we found some cuts in the fences, and there's people sometimes living back here in homeless shelters, homeless encampments. Global Marine. So anyways, oh, and Sims. So Sims had no beach. This is the backside of the metal recycling plant, where it's owned riprap. And it still had fish in it, though. There were still some mummy chogs when you did trapping them. So this is Bayonne Golf Course, where there's been some mitigation effort. And this is right adjacent to the boat ramp at Liberty State Park. So Liberty Golf Course Club is down here with the bulkhead. And so very close to marsh, but there was a lot of mummy chog and striped bass and stuff right along this, when you sang this cobble here, they were there. Okay, enough of pictures. At these sites, we looked at salinity, temperature, the water quality metrics. I'm not going to push those all up right now, other than to say, because they're coming up in a later analysis, that they were fine. Even dissolved oxygen was never at stress levels. So that's a good thing. The other point is that they were all very similar in temperature and salinity, not over time. There's great variation there over time, as you expect from an estuary, seasonally and with tide. But if you went to a particular place during the high tide, the adjacent ones were also similar to it. So they're being serviced by a tide, a common tide current that then receives pulls water back out. We looked at sediment from cores, and it was principally sandy. There was some differences there. We did bring this in. And so do they hold fish, and are fish reproducing? So are they nursery habitat? This is results of a canonical correspondence analysis. It's similar to a PCA in the way you read the graph. It's a little bit different. It does bring in the environmental factors as well. But what we see here is there's a number of fishes. I think we had total of 32 different species of juvenile fishes that we found here. So diverse. You see some differences, meaning you tended to see Atlantic silver sides at a site different than where you'd find tomcods, so there was some spread, but the spread is very weak. If you look at the eigenvalues, they explain variance of this. The total of the first two eigenvalues, which are the really important ones, are still coming up to only 25%. So the total of the 19%. So it's very, very weak. And what that means is that there's very little statistical confidence in the difference of fish assemblages among these sites. They're all acting similarly in terms of the fish that they are holding. I'm sure everybody else appreciates that too. Brown. When I plot these samples, by the way, these are in the same space here. I've just taken the sample plot out so that you can actually read it and duplicate it. These are the same samples in the same place, but they're coded different. So here you see that the spread that we get is essentially a seasonal spread. It can be explained by different seasons, and no surprise there. And that what you see here is a huge overlap among sites. Okay? The sites are coded by color and then wrapped by an envelope. So there are some sites that at times, probably due to season, have some different outliers, but principally what we're looking at is that all these sites, both the restored sites and the accidentally restored sites, are acting as fish habitat with fairly little difference in confidence that they're different from each other. Here we see some of that spread in what's accounting for those things. We have this outlier here. This was one sample that was characterized by very, very high catch of Atlantic menhaden at Liberty State Park. And what we could see there was that at that time there was effluent of some kind, drainage coming out of the golf course and entering the estuary there as a very, very bright green stream. So this was an algae bloom of some kind, almost really bizarrely green. Cyanobacteria or something that's coming in probably because of liming or fertilization. So the pH was very high here. And that's consistent with liming of the golf course turf and coincident bloom of algae. And that may have attracted these, which are filter feeders that often feed on algae, to this area. But it could also be entirely stochastic, because these are fishes that bunch up into huge schools and you could either catch them or miss them. So in general, again, the take home is that there were not big differences in sites of the things that could be measurable. When you measured them, neither was there a big difference when you're looking strictly at the latent, meaning the underlying fish assemblage, without trying to account for why that might be. And here's the example of the fishes that we found that were at least relatively abundant. And in a pictorial sense. So you can see here the effect of time. These are ranked. Atlantic silversides were the abundant forage fish, most abundant fish. They're abundant everywhere. They could be found in open water, especially in calm open water, but they also come right up into the grass. They're kind of generalists. They lay eggs along the grass. They prefer laying eggs on algae that's attached to walls or on the actual flooded marsh grass. We did not find eggs of those. We went looking for them, but the eggs, when they hatch, the larvae get redistributed. Also, the adults of this particular fish leave out to the ocean, actually coastal ocean, and I've actually caught them well out to sea during winter, and then they come back as adults back into the estuary and lay their eggs along these sites. So there's no surprise that they should be abundant or that they should be in these particular places. What is surprising and encouraging is that there were many. Second most abundant animal here is mummy chalk, Fungulus heteroclitus, which is a benthic substrate spawner. It's essentially marsh obligate, and there were plenty of them there. So, you know, that was a big question. If you have this marsh-like habitat, that doesn't mean you have them there, because have they recolonized it? Or if they have, is the size of the area big enough to sustain a population there? So for that, we have to go to the next step. But before we go there, I just want to mention that in this group, you see fishes that are not spawned here at all, like Mugilcephalus, which comes up right in the Gulf Stream, has larvae, and then recruits here and grows. This is now called flathead gray mullet. It used to be called striped mullet. We also got white mullet, but bluefish spawned out in the ocean. Winter flounder, which are spawned typically in the lower estuary. They might move up into the estuary too. And spot, which are spawned offshore also. Of the abundant sentinel species, oh, by the way, blue crab is another one that is spawned. The adults move to the head of the estuary, spawn or drop their fertilized eggs there. The eggs and larvae hatch and move out into the ocean, the coastal ocean, and get trained back in, sometimes not to the same estuary. But they were very, very abundant there as little settled crabs. So these things are serving as habitat, nursery habitat for fishes and crabs that are local to the estuary, and also that are transients or not local to the estuary. But this is where they have to stay. They can't move until winter when they're big enough. So we wanted to see if life cycle is actually being completed here. And we found that for these sentinel species, we found all stages. So for mummichogs, we found eggs. We found larval Atlantic silversides, and these are basically the pulses from very, very small fish, and you can see them in multiple modes, showing that these fish are growing and surviving here over time. I'm going to wrap this up. We also tag fish. 1,100 or 1,200 mummichogs with micro wire coated tags. These are tiny tags. If you've ever used a mechanical pencil and broke the little lead piece that goes flying, the tag is even smaller than that. It's injected either through a needle from a handheld gunner, in this case a machine one. So she's got this little mummichog right there. She's holding it up to, and it sticks it in there, and it has a tiny, tiny code, and you can detect those with a wand, a metal detector. So when you go back a month later, you can get a bucket of 200 or 300 of these, wand it, you'll know right away if there's a tagged fish in there, and then you can separate that in the aliquots, separate it by half, very quickly break down and get the fish and get the tag back out and read it. And what we found here was that we tagged heavily at 2 sites, and all recaptures were within the sites that they were taken, not even at adjacent sites. And the recaptures were very much in line with what we could tell about the total population size. So you could, in theory, use this, and we did do a calculation from multiple recaptures that tells you about how many fish you have there, and the recapture rate is related to the size of the population. If you have a very large population, you're less likely to recapture a tagged individual, because you're recapturing a different individual as a percent of the population, and that's reflected here. So Army Corps Basin had a smaller population than Alexa City View, which is the restored side of that Bayonne Golf Club, a huge, huge area there. Okay. Finally, what we want to do is put this together. I promised to come back to this thing, which is what we're working on now, understanding the contribution, knowing that there's fish in all these kinds of places and what kind of fish there are. What really is the contribution in area of these? And I think that this is a survey application, not a science project where we're testing a hypothesis, but I thought it would be very interesting to put into a synthesis of this, because this comes down to decision-making by regulators or planners or anybody that wants to know what kind of impact they're actually going to have and how to prioritize these things. So we did this shoreline analysis that was made possible in large part because it coincided with this report coming out on shoreline survey. This is a digital elevation model and side scan survey of parts of New York Harbor for the park. So what is the distribution of that bathymetry? What are the sizes of the coves between the piers? How do they relate to the total area, the average depths relative to the different shoreline classifications? And we're in the middle of this now, but just to show you where we've gotten, this is the area of the shoreline in green on the New Jersey side, and the blue that we have surveyed from site visitations and classifications from aerial photography and maps to particular types of shoreline. And then in this pinkish color is where we have the benthic survey adjacent to those sites. So we can ask different questions of different areas, and the answer is going to be biased to the area, but it's still very interesting. So to get a close-up of that, this area where there's a benthic survey right adjacent to the shoreline, we have bathymetry or digital elevation model, and it goes right up to a shoreline. So we can ask questions about the distribution of depth relative to shoreline structures. And this is it without the underlying layer. Oh, they go backwards here. Here you see another close-up of it again. And one of the issues we're dealing with now is where this hasn't been extrapolated out. We have to come up with an algorithm that gives a probability from nearest neighbor to the depth. So we do have depth here, but not right against it. And here is your basic first result of that, the average depth relative to shoreline classification. So at your covered passable structures, these are piers, basically where water can go underneath them, or kayakers, as we did, can go underneath them. Your average depth is around 6 meters. And, well, I won't read them all. You see that vegetated shorelines are tend to have the shallowest average depth. Probably no surprise there. Sand and gravel next, and so on. So these will help. I haven't put them into context right here, but essentially we anticipate looking at this in context of how to prioritize areas for restoration and stuff. This is the depth frequency distribution of shoreline along shorelines. So you see that we have shorelines with depths down to 26 feet, but it makes up, probably 20% of the total, where you also have about 20% of the total shorelines where you have quite shallow water, and that's a good thing.
How are you describing the shoreline? It's distant, like some set distance off the shore, or is it pierhead to bulkhead? Or?
This is within a raster pixel alongside the shore, which I think these were 1 meter raster. Good question. So the last thing we're doing now is we are quantifying the aspect ratio, distance from shore, and total area of those particular coves, so that we can put them in the framework of how much area these piers are actually shading. And that addresses this kind of question about that Bone brought up in 76, that these were trapping sediments and making the water stagnant. But as the river water itself is cleaned up, the waters that are once stagnant become calm waters. The kind of waters that we typified with the Didson as having many, many more fish. So those potentially could be habitat. And when you think about that, then the pier, well, what if that pier was solid? Well, it's even worse as fish habitat if it's solid, right? There's definitely no fish under a solid pier. And yet we've thought of that as good, in the sense that it's not the habitat directly under the pier, but it raises the quality of the habitat next to the pier. And the question is, how do you get that ratio right? And when does it become right? And that's where I was asked to testify at a hearing, a case for an individual homeowner who had they extended their dock 4 feet more than the permit. Okay, and I don't know the outcome of this, but they asked me a lot of questions, and to me, not being a legal expert, I was wondering why they didn't just focus on whether it was permitted or not. It wasn't permitted, but this question came up, was this 4 feet of that extension degrading fish habitat? Because we had publications that said that shade degraded fish habitat. This is shading an area right here where you can clearly see water. You know, the water was very shallow, typically like that. It was dry at high tide, wet at low tide. There was algae growing on the back of the pier. This was fundamentally different than the stuff that Ken Abel and I had done on piers, where the water here is 6 meters or more, and the interior of the pier is darker at the surface during the day than the outside of the pier even is at night. So, and the question was also, what about herring and menhaden that are out in the water in front of this homeowner's house? I can't say that did anything to those fish. That's not something that we studied, but it's also in my larger kind of experience. The shading that you saw at this dock is very similar to where we've been setting killie traps underneath our, along our station docks for 29 years and catching lots and lots of mummy chops there. So it's a different question. Now I understand and fully appreciate the concern of the regulatory agency, and am not dismissive of this effort by the regulators. There needs to be some understanding of what this is, because I can't answer that question. Somewhere there must be a gradient or something, or a threshold that says, well, this doesn't matter and this does. In the absence of that, the regulators are right to just say, well, that's shading fish because somebody said it shades fish. This is a graph, by the way, of light underneath these piers here. Even at noon, at low tide, when there's maximum light penetration, the light would sometimes not reach the level of that's detectable by an eyeball of a fish. It's absolutely black. And that's not the case along that dock. So the last thing, the place where I want to go next, with future funding and stuff, we haven't started this except as models, is to look at a new concept in ecology called scaling. This is to ask the question, at what map scale does distribution correlate to map features? Here's a quick example from Machinatoneo's paper here. From a model, you can connect these in a hypothetical track, these particular features, and this animal, elephant, is very attracted to the particular features. It makes them destinations to go to. But at a different map resolution, you see that it would seem to avoid those. In this case, we're talking about elephants in savanna forests. They highly value shade trees, but they do not like closed forests. They like them at this intermediate density. And coming back to this concept that you can't cage a fish underneath a pier, but potentially pier is beneficial for part of the life cycle, or the proximity of a pier is beneficial even if the area underneath the pier is not beneficial, is an outstanding question that could be addressed by spatial scaling analysis. So this is where I'm going to end the particular talk. Just want to wrap up with this. If you look at this, it might be astonishing that there are marsh fishes left in this area, especially because we don't have this side anymore either. It's all like that. But I come back to remembering that the most important thing for fish is water. So, you know, that's there. The water is healthy. So that means that it's available to use for these things that are annually reset. So most of the fish that we're talking about come from elsewhere. They recruit here. They can use it if there's suitable habitat for them. They can grow here. If something terrible happens in one year and wipes them all back out, that same place could potentially be habitat again the next year because it's an annually reset assemblage for the most part. The exceptions, of course, are mummy chog and striped killifish. So there's lots of resilience in the system because of that. I think that cleaning up the water was the first major hurdle, and like we're there. Like this is substantially cleaner water. It can support fish. It is supporting fish. There's ways to work that nursery habitat model into these systems here. And it's a matter of understanding cost benefits and space areas and things like that that come into scaling. So that's it. Want to thank especially Hudson River Foundation. They've funded us for years on this work. A lot of technicians, interns that we've had through our research experience for undergraduate interns. Jim Gill, a harbor master at Pier 40, was very helpful when people with guns were chasing us away, making us not survey there. And Army Corps of Engineers gave us dock space and also supported us on the water. Also, Coast Guard Group Bayonne, very helpful in that respect. Global Marine gave us a tour of their facilities, talked about that. Bayonne Golf Club, likewise, Ron gave us a tour of the facilities and stuff. These are the techs looking for eggs. They're doing egg survey here back. This is the Army Corps of Engineer embayment there. So we loaded with trash, plastic trash and stuff. Fish don't seem to care. Of course, we haven't done anything with ingested plastic or anything, but certainly these big chunks, they're spawning and stuff sometimes on them. And I think it's the products that break down that are especially harmful, or when these things land on the grass and flatten the grass, you get pieces of boats and stuff in there. That could stand some cleaning up. Questions? Questions? Yeah.
Of the difference between immobile armored structures and softer elements that are more ephemeral and are moving and building them.
We don't have cores right alongside those, but what we found is very similar to I meant to mention this. There's a whole bunch of papers that came out in a row just about this time that are syntheses, and that was the result of a large program called CCOR, C4 it's pronounced, that came principally out of the Target's lab at Delaware. And the overall goal of this project was to look at cumulative effects. You can have a dock, you can have two docks. When do you have too many docks? again, this is very tied to the spatial scaling issue I was talking about too. And same thing that happened at the same time, 3 or 4 synthesis papers came out from Seattle area. And all of them came out at the same time we were starting this synthesis project, which is why I kind of changed a little course here. They all said that you can have fish here, but you're very quickly changing to an offshore assemblage, so a deep water assemblage. So right up to the pier edge, it's not the fact that it's a pier or it's a bulkhead or it's rock. It's simply the fact that it's deep that matters in those cases. Now, secondarily, when you look at things like mummy chog, you need to have spawning area, and they will spawn on a number of different things like mussels attached to bulkheads, so you can still have them there even if you don't have marsh. But they're not likely to travel deep water between coves. So the bigger the area matters. But sediment, we didn't sample the difference between sediments at the bulkheads. We were sampling sediments at the beaches, the relic beaches or newly formed beaches that were behind them. So that's as good as I can give you for that. There's a lot of work on that, and people do it, but I don't know how it contributes to benthic fish. Yeah.
Is that Hudson equipment expensive?
A Didson unit costs about $84,000. I don't know if that's expensive or not. It depends who's asking. To some people, that's very cheap. We rented ours. We rented it at $500 a day, including the return date of travel shipment. And it comes in 3 boxes, so it's about $55 to ship either way too. So yeah, it could be cheaper to buy it. It could be cheaper to rent depending on the number of days you're using it.
The other thing is, you mentioned the increase in menhaden. Do you have the date on that?
That was the difference that we noted here in this harbor was between 2011 and 2012. Huge jump then in that Hudson video. So measured that way. There are good records in fishery. That's a monitored fishery, and there are good records of menhaden population in general.
Well, that's exactly the time we saw the increase in whales coming back.
That no surprise at all. Yeah. Yes.
My Tea Party friend says that global warming is a hoax, but I'm just curious. We had 90-degree water up in Haverstraw this summer, and I was just wondering if that affects your activities in any way.
It does. We have been monitoring larval ingress at Tuckerton and juvenile fish settlements trapped in Tuckerton for 29 years old. So this year will complete the 30th year. Weekly. So weekly ingress. Only 2 days that we missed out of all those years was Hurricane Sandy and one time when the ice was too thick to break through. Since '96, we've also had a record every 15 minutes from permanent loggers installed in the system, 4 of them. And what we've seen that since 1997, when that record was first full year, to 2016, when I did this analysis, our water temperature in the bay had gone up 3 degrees on average. Annual temperature, that's 0.1 degree per year. And as you went upriver, you saw an increase in all ones up the watershed, but they were not significant and they were less steep as you went up. What that means to me is that we're seeing a warming effect that is driven principally by water in the lower system, which is tidal coming into the ocean. Whereas water temperature that's influenced most by the watershed itself is rising, but not as steeply and not significant. So that's the first part. We're seeing warming, we've documented it. The second part, and it could go back on a down cycle, but this includes 3 decadal cycles with We have documented a change in the timing of arrival. First arrival, 50th percent arrival, 85th percent landmark, and the difference between first arrival and last arrival at those landmarks of larval fish entering the system. So, winter spawners are arriving later, some of them many, many days later per year already, like American eel, whereas summer spawners are arriving earlier, and spring spawners are arriving earlier, and the dates between the first arrival and last arrival are spreading out, so they have long intervals. Additionally, looking at the assemblage, we have seen a change in the species of fish, and these defy your basic trend analyses because they weren't even here in the previous years at all. They're showing up now in abundance suddenly. So it's very difficult to run a trend line through them because they're not lower abundance to higher abundance, it's just all of a sudden they're abundant. And so that means a different, like a broken stick analysis. And then finally, fishes, the assemblage where fish have been here, we have seen significant differences in species abundance relative to each other, and it does correlate with the temperatures that we have, and not with rainfall. It does with temperature and some other things like wind, I think, winter wind, something like that, which has to do with transport. So those things they're in publication now, but it'll be a while before they come out. Yeah.
Just a clarification, Mats, you described your fish communities based on, or what's in different sort of habitats, and then you also did some analysis of abundances offshore.
Relative to this
Relative,
offshore, yeah.
But you didn't do anything specifically for water depth. Is that what you're going to get into? I mean, I raised that question.
Right.
I remember Ken Abel sitting in his room, a number of years ago, said,
we need shallow water.
We need more shallow water. Is that still the case?
We need more shallow water with shoreline. So I didn't talk about it. We did look at Jersey Flats, and there's a problem. We can't seine Jersey Flats because there's no place to haul the seine up, right? But the Dixon data shows a lack of the same. I mean, it looks different than the cove sites for sure. Menhaden, striped bass, and bluefish there. Again, that's a typical deeper water offshore, not offshore, but off beach assemblage. And that's again consistent with the things coming out of Target labs and other labs like that. There needs to be some sort of a boundary or a shoreline. There's some kind of shoreline service that comes from that. I'd really like to get more into that. One thing that I haven't seen anybody do yet is microscale temperature measurements. When you wade in this water barefoot, you'll be in water that's very hot, like up to your ankles, and you step even a little bit deeper, and all of a sudden, like your knee is warm and your ankle is cold. Because there's this very thin layer, like that thin. But that thin, that's the kind of water that we're talking about as prime nursery shallow water habitat. And when you have a very flat place, you can have a very big expanse of that. And when it's steeply sloped, you have a small piece that moves up and down with the tide. And I think this could be important because there's a very well documented relationship between temperature and growth rates for fish, which are cold-blooded. And they could be up in that steamy water because of that higher temperature. Many of these are annual fish. They have a year to grow and reproduce, to lay eggs before they die. Some of them make it the next year, but it might be really beneficial. If they get 4 extra degrees, it could be everything.
We have maybe a question from
folks
in the webinar. Is that a question?
No.
Okay.
I've got a question for you. In your introduction, you talked about this being a perfect zone, I guess, osmotically for the species over here. Would you imagine that zone would have been further north historically before there were all the CSOs and development, or is that just changing the frequency and variation only as opposed to the overall average?
Well, this work comes from, actually work that was funded also by the Hudson River Foundation, not by me, but by a colleague of mine when I was in graduate school. This was Conover and Tom Hurst lab. So even annually, you can see a big change in where that zone moves up and down, depending on if it's a drought year or not. And it turned out that when the city pushes, the city gets a lot of snow, and all the snow from the interior Manhattan gets pushed over the edge into these shallow water areas where those relic piles are, and the pile fields that are sheltering those overwintering striped bass. That can drop the salinity of the water very abruptly, and in order of like how much it drops it fast and it's big. And that's a concern. I don't know what the CSO, if snow contributes to it, I suspect that especially in near shore zone, that freshwater outflow from other sources also could, but it's not something I've measured. We see big swings in the tide though, like, follow the tide up. In fact, the way we sample, we try to stay always in the same tide zone so that we wouldn't be biased.
One more?
You mentioned this already, but do you have a rough estimate of when your shoreline analysis would be available?
Yeah, when?
Or how to be updated on?
Yeah. Good question. Let's yeah.
You're on the webinar.
Let's say June.
Okay.
Yeah, it won't have gone through peer review, because that can take a year in itself, but we'll have it out as a white paper then, I think.